So the normal modes of oscillation near equilibrium. Ooh, not that pen. I was using the wrong Apple pencil. It's like you've got, I mean, the way I picture these things is you've got a system and it's got some potential energy surface, and the potential energy surface might have different kinds of features in it. So from the potential well in n dimensions, n degrees of freedom, so from a potential energy surface in n degrees of freedom, and just 2 are shown here just for convenience. All right, we got, this is our potential energy, a couple of coordinates, and we're just sort of showing you a slice through so you can kind of see where the interesting features. It looks like there's a, maybe there's an equilibrium point there. We want to know what are the motions near equilibria. And there could be unstable, which means exponential growth, or stable, which means oscillatory. I guess another type of, then there's like neutrally stable, which means just moves the constant speed. Those are sometimes called rigid body modes. So, for example, if we had a double pendulum, it's got one equilibrium would be a double pendulum, double planar pendulum. We got our 2 things, the 2 links going downward. So that's equilibrium. If you were to solve for the modes near this equilibrium, you would get 2 mode shapes. These are natural modes or normal modes. These are the purely periodic modes. And one of them is that this link stays rigid and the thing just sort of moves as if it's one pendulum. So we might call that mode 1. And then another mode is that as the top link goes one way, the bottom link swings the other way. So if we go, this goes that way, this goes this way, then we call this maybe mode 2. And it'll have a different frequency. They'll tend to have a different frequency. We might call this the in phase mode. And then this the out of phase. I mean, the names that you give things depend on the context and what it is. And it turns out that any small, if I were to just sort of tap this thing near equilibrium, so I've got some initial condition near equilibrium, the motion will be some superposition of these 2 modes. So this is just reintroducing something we discussed in the last lecture. And then if you remember the setup, so this is just a recall from last time. We had a we got a 2 matrices, one that comes from the kinetic energy and one from the potential energy. So we had that the kinetic energy is equal to 1/2, and we were using this delta Q dot T, delta Q dot, and the potential energy U is 1/2 delta Q U delta Q, and there's a transpose here. So delta Q is just a column of displacements in each of the generalized coordinates. Okay. And I guess I was using capital N because it's equal to the number of degrees of freedom. All right, all right. And then once you've got these, the T and the U matrices, you're able to solve for normal modes, or first solve for the frequencies by calculating something that looks like an eigenvalue problem. You would do the determinant of U minus lambda T equals 0. Solve for the lambdas. And we'll refer to, lambda K as omega K squared. If omega K squared was greater than 0, that means oscillation. If omega K is equal to 0, this is a steady drift. And if omega K squared is less than 0, this was exponential growth. You might think. That if we have cosine omega K T, in this case, omega K is equal to the imaginary number I, alpha, where alpha is greater than 0. So cosine omega kt equals the hyperbolic cosine of I omega kt. That's just an identity. And then that means this equals cosine, hyperbolic cosine of negative alpha t, which is 1/2 e to the alpha t plus e to the negative alpha t. And the solutions that we assumed, so we have solutions of the Lagrangian equations near equilibrium of, it looked like delta qj t equals Caj cosine omega t plus phi. So that means this term goes exponential for the omega k squared less than 0 case. Okay. I mean, what it physically means is that looking back up here at this potential energy surface, you would be at a saddle point. So I don't know where there's a saddle point here. Maybe it's like there. So if you're at a saddle point, there'll be like a stable direction, but then there'll also be an unstable direction. And so the unstable direction will give rise to exponential growth of any small perturbation in that direction. So exponential growth, this has to do with, saddle points. Or actually, and hilltops. If you have a hilltop of the potential energy surface, then all directions are exponentially growing. Okay, so we're gonna try out this on an example, simple example. We've got two masses. Check it out, two masses. If only these masses were connected by springs, then you could really see it. So here's the two masses. So here's an example, 2 degree of freedom system. we've got, let me sketch it. You could think of it as two masses in carts connected by springs to the wall, both walls. And we'll say that these springs have equal spring constant. And there's a we'll say that Q1 and Q2 are measured from equilibrium. So that's the displacement of each of these masses. Q1, Q2. So Q1 equals Q2 equals 0 is an equilibrium of the system. This has, because we've got these two Q's, this has 2 degrees of freedom. Oops. 2 generalized coordinates, and therefore it must also have 2 normal modes. So we want to find out what those normal modes are. So step 1 is write the kinetic and potential energy. Potential energy near equilibrium. You know, and just as a note, we're not using the deltas here because we've already chosen our coordinates so that, you know, delta Q1 is Q1 and delta Q2 is Q2. So we don't have to use the delta notation. All right, so the kinetic energy, and this is just the straightforward kinetic energy. Everything's moving just in this one dimension, the horizontal dimension. So we would have 1/2 m Q1 dot squared plus 1/2 m Q2 dot squared. And now we want to write this in terms of a matrix, and it has to be a, right, we want the symmetric T matrix. So we will rewrite this, and it has to be, we're looking for something that's got the form we're looking for the appropriate symmetric T that would give rise to this. And here's the T. It's pretty easy. It's just, looks like the identity matrix, but it's got M's in both slots. So notice that it is symmetric, so we're on the right track. If it wasn't symmetric, we'd have to start over. And in fact, it's not only symmetric, it's positive definite. And that's true for the kinetic energy matrix. T is always positive definite. So that's a stronger condition than symmetric. Symmetric could have other things going on. Positive definite means that we're always going to get something positive for T here, or 0 if both of the velocities are 0. So that was the kinetic energy. Let's get the potential energy. This is going to be tricky. All right, so we need to look at, there's 3 springs, so it's the stretch in each spring. So the stretch in this first spring over here, that gives us 1/2 K Q1 squared, stretch in the spring. And just to make life easier, let's do this other spring on the end, the other end. So this will be plus 1/2 K Q2 squared. And then, dealing with the troublesome spring in the middle. Well, it's not that bad. It's 1/2 K, but then what is the stretch in the spring? It's actually Q2 minus Q1. That's the stretch squared. Okay. So you work all that out, and you want to write this in the form of 1/2 the Q's transpose times the U matrix and Q's. And here's what you get. And you need to make a choice so that this is symmetric. And what do you know? That's what you get. Again, notice it's symmetric. Now the potential energy the matrix doesn't have to be positive definite, but it does have to be symmetric. So again, if in doing your stuff, you get a matrix that's not symmetric, that's a sign to go and try again. Okay, so now we can solve for the frequencies. We've got our matrices, T and U, so we're good. All right, so step 2. Solve for the natural frequencies. So how do we do that? Well, we'll write determinant of U minus lambda T, right, equal to 0. And right, the lambda equals omega squared. It's easier to just work with lambda when we're doing this though. So let's do this. If you write out what is this determinant, you'll get that it becomes K minus M lambda, 3K minus M lambda equals 0. So that's our characteristic equation for the lambdas. All right. So the frequencies, no, one of the masses fell. You'll just have to imagine it. Okay. So the frequencies are the roots of this equation. So we've got lambda 1 equals omega 1 squared is K over M. Lambda 2, we'll call that omega 2 squared. It's 3K over M. Okay, so we've got these two frequencies. Yeah, so omega 1 is square root K over M. Omega 2 is square root 3K over M. And then we solve for the mode shapes. And then sketch them. Solve for the natural mode shapes. Those are those vectors A from last time. And sketch them. That's something you can do when your degrees of freedom isn't too high. If we're talking about, like, this same process gets worked on large pieces of machinery. Imagine a finite element model of a vehicle, a car, a GM car with 1 million degrees of freedom. And there's a whole industry of trying to find out what the modes are so that they won't be excited by the rotation of the wheels and other things. So yeah, it'd be hard to sketch that, but we start with simple things so we understand the principle. Okay, so we'll do the mode shape for what we've kind of arbitrarily called mode 1. That's the one with omega 1 is square root k over m. All right, and that means you plug back into this equation, and it's like solving for an eigenvector. And here, instead of lambda, we've got lambda 1, so k over m. Okay, and what does this become? This becomes, we'll be left with a matrix. This is what u minus k over mt gives us with all of the constants pulled out. So we're just left with this. What is A? A here is, it's a 2 vector. A1, A2 equals 0, 0. Okay, so from this, we can notice that we've got A1 minus A2 equals 0. That's what, we've got 2 equations here, and they're giving the same thing. So that means that A1 equals A2. So the mode shape here, and we could just write it as 1, 1. It's telling us if there's displacement in the Q1 direction, a certain amount, there'll be displacement in the Q2 direction, the same amount. So here's 2 masses. Got this silver thing. So that means if one of them moves, the other one moves. So we have a mode that looks like the 2 masses are just moving in sync together. So if we were to just sort of sketch what it looks like, we've got our masses and springs, and these 2 masses will move together, and they'll oscillate together. So we could call this the in-phase mode or in sync. It's as if there's just one mass and it's moving back and forth. So that means if we were to pick up both masses, move them the same amount and let go, it will just oscillate with this frequency up here, omega 1, forever and ever. So now we could solve for mode shape 2. Mode shape for what we've called mode 2. This was that one. So u minus 3k over m t a equals 0. And so there's a question, can this mode shape be called a rigid body mode? I guess you could. I mean, just in terms of a name. Yeah. Often the rigid body mode is reserved for omega equals 0, because that would be steady drift. But this one could also, just because of its appearance, I think be called a rigid body mode. So I don't know if there's any hard and fast rule. From this, you would get, I'm not going to work out what the matrix looks like, but I will tell you what you get for what the 2 modes do. So it's A1 plus A2 equals 0. So instead of a minus, it's a plus. So what does this mean? This means that A2 equals minus A1. So this second mode shape, we'll do A vector subscript 2. It's 1, negative 1. which means in terms of sketching the modes, if Q1 increases to the right, then Q2 decreases the same amount. So going to the left. So that means in this case, if you were to displace these exactly opposite, then they'll both oscillate out of phase. So this is the we call this the out of phase mode. I mean, I'm naming it that. Nobody's gonna tell you to name the modes right. So there we go. Simple enough. And this will oscillate with a higher frequency. Right, it's going to be, in fact, the ratio of these two frequencies, omega-2 over omega-1 is square root of 3, which notice it's irrational. What does that mean? Okay. And this is a key point. Is that any general motion of this system near its equilibrium will be a superposition of these two modes. Any motion, which is, kind of weird. But that's just how it is. So we'll have the sum of these two things, if you want. Let's write, Q as a vector, as a function of time, is going to be A1 as a vector. And then, well, there'll be some overall constant. Maybe let's put a constant out in front. A1 cosine omega-1 t plus some phase plus C2 A2 cosine omega-2 t plus some phase. So it looks like the sum of two sinusoids, but with different frequencies. What will that motion look like? I'll show you. Let's go back here. Yeah. So this just sort of shows what the general motion would look like for a little while. It looks like some kind of oscillatory pattern, but in both directions. This is V1, but what we mean is like that mode and this mode. So mode 1, mode 2. If you start with some initial condition, you're going to look like what looks like a pattern that appears this way. And these trajectories are called, does anybody know? It's got a name that starts with L. Lissajous. I think I'm saying it right. Lissajous figures. And they're related to Chebyshev polynomials in some way that I will not get into. But maybe you've heard of Chebyshev polynomials. Just a little bit more on on those things. Yeah, so this is showing some Lissajous figures for different values. This rho parameter, this rho is equal to the ratio omega-2 over omega-1. And so if you have some rational number, you'll have Lissajous figures that can possibly close up. This is showing that they've got the same phase, and this is showing some arbitrary phase. But maybe you've seen this type of figure. In general, so this is showing rational frequency ratio. If you have an irrational frequency ratio, and you know what this is in the directions of the modes. Let me show. You get something that seems to fill a rectangle, and this is far too much to show. There we go. There we go. Rational. But you can kind of see it's like filling stuff up, and you've got these two sinusoids, but they seem to fill a space. They seem to fill a rectangle. So this is in 2D. You could have Lissajous figures in n dimensions. In fact, this idea of Lissajous figures and the superposition, this is true in n dimensions. So this superposition of modes is true in n dimensions. It means n degrees of freedom, but we're only showing it for just to give you some idea of what things look like in 2D. Okay. Let me give you some other information. This is I don't know if this is an intuitive picture, just another kind of geometric interpretation. So if t, well, t is already positive definite. If u is positive definite, that's the same as saying that all the omega k squares are greater than 0. So everything is actually oscillatory. That was the case for this example. And let's just limit ourselves to that situation right now. Then we've got the equations that we have look like Q, I guess we did delta Q double dot T delta Q double dot equals negative U delta Q. That's what we got. This was the Lagrange's equations near equilibrium. But if U is positive definite, then we could write this as delta Q double dot equals, and I'm going to use matrix K. K equals T inverse U. And it's a truth, a mathematical truth, that if T is positive definite, if a matrix is positive definite, so is its inverse. And the product of two positive definite matrices is also positive definite. You're like, okay, big deal. And think of the two-dimensional situation. What you should be thinking of here is that this looks like Newton's second law. Second law for a particle of mass m equals 1 in a force field. I'll write it as F negative K delta Q. Okay, and let's sketch what that force field looks like for just 2 degrees of freedom. In 2 degrees of freedom, this is what that force field looks like. I got a picture like this. So this is just showing the planar case. You can kind of generalize naturally to the n degrees of freedom. But we've got, this is an equipotential line that we're showing. So that means it's, you know, the potential energy U equals a constant. And then we're plotting, the arrows are the force field. And of course, your eye is drawn to these eigendirections. So those special directions where the force points towards the origin, right? And here, when you've got the force pointing towards the origin, you'll have K. Those are the directions where if you were to displace by some vector, right, this equals lambda V for an eigendirection V. And here, these values, eigenvalues lambda, are playing the role of a Hooke's constant. Because then along eigendirections, it's like we just have a one-dimensional Hooke's law for a spring system. So it's like we've got a spring mass system embedded along the eigendirections of our problem. And of course, this will give rise to sinusoidal motion. And those eigendirections are the normal modes of vibration. All right. So that's just another take on things. Okay. I guess I should say something about these normal modes, because we don't have to stick with the original delta Q directions. We could actually use the normal modes as the new directions describing our system, right? Why be stuck with things like if this was Q1, or I guess delta Q1, and this is delta Q2, that's supposed to be exactly vertical and exactly horizontal. We don't want those directions. We'd rather use these eigendirections, because those are kind of the natural way to describe the system is in terms of the eigendirections. Maybe physically it's convenient to use delta Q. Maybe that meant like horizontal displacement and delta Q2 meant vertical displacement. But the eigendirections are more kind of natural to the system. So we can use the modes themselves as new generalized coordinates, even though they might be mixtures of pure kind of physical directions. And so these are the normal modes that we're talking about. So normal modes. So let's go back to the spring system up here. Okay. This spring system, notice what the modes were. We had the in phase and an out of phase. So we can introduce coordinates. We're going to introduce normal mode coordinates, generalized coordinates. So we'll call it x1. x1 is 1/2 q1 plus q2. This is the generalized coordinate for mode 1. And there's a systematic way to do this for any degrees of freedom. I'm just kind of introducing it, all right? For mode 2, q1 minus q2. So remember what this mode was. This was the moving together mode in phase. So generalized coordinate for mode 2. This is the moving opposite mode. These are called normal mode coordinates, or sometimes just called normal coordinates. And like I said, we could treat these as generalized coordinates. And one of the powers of the Lagrangian formulation is that you could use any generalized coordinates for writing your Lagrangian. So if we were to write our Lagrangian, instead of using the q's, we could write the Lagrangian for our system in terms of these normal coordinates. Now, this is the Lagrangian near equilibrium, but it looks particularly nice. We have 1/2 x1 dot squared plus omega1 squared x1 squared. What do I mean it looks particularly nice? Well, there's no coupling between the two sets of coordinates. Lagrange's equations for the normal coordinates are uncoupled. Meaning there's no term from the Lagrangian itself, you could see that there's no term that's like x1 times x2, which there was in the original coordinates. And you could see that from the form of the matrices. Here, the t and u matrices would look very, very simple. And the equations of motion we get are very simple, right? We've got that, and then we've got this. Uncoupled. So motion in mode 1 only is going to look like x1 as a function of time is, some constant cosine omega 1 t plus a phase, and no motion in that second normal coordinate. Same thing, motion in mode 2 only. x1t is going to be 0, and x2t will look like some constant cosine omega 2 t plus v2. So the power of normal coordinates is that it shows that the motion in the two different modes is completely uncoupled, and this generalizes for n degree of freedom systems, where you would get x double dot plus omega k squared x k equals 0. K goes from 1 to n. So that's the power of normal coordinates. Things that otherwise might look like everything's coupled, you can decompose it into these uncoupled pure motions. And then any arbitrary initial condition is just going to be a superposition. Here, the superposition is easy to understand because it means, okay, x1, the x1 mode is excited, and the x2 mode is excited. There's another way to view this, because looking at these equations, right, we have that in each of these, it's almost like we've got two separate systems. We've got two separate harmonic oscillators, and the energy in each mode is separately conserved. So that's interesting. Whoa, 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 okay. Energy in each mode. And so this, like, some people talk about like, oh, the mode in the energy in mode 1 and the energy in mode 2. And if you do kind of a nonlinear version of this, you could have the energy from one mode going into another mode, and that's kind of interesting. That's related to parametric resonance and other types of phenomena. But we're looking at the case of, we're very close to equilibrium, so we don't consider nonlinear terms. So everything does naturally decompose. What is the energy? And so this was just kind of on the side. Yeah, this generalizes n degrees of freedom. Great. For this, we've got that, x1 dot squared plus omega 1 squared. I'll write it this way. x1 squared equals 2e1. That's the energy in mode 1. And x2 dot squared plus omega 2 squared x2 squared equals 2e2. It's the energy in mode 2. So they're separately conserved, and there's a nice image that we can see. If you remember the phase space for an oscillator, a harmonic oscillator like this. Well, now we just have two oscillators. So here's the two oscillators. So we've got the two phase spaces and then conserved energy. So this would be like the contour related to energy E1, and here's contour related to energy E2. And we can use these phase angles, because if you're on a particular energy, all that really matters is the phase in the oscillation. So we're using this theta 1 and theta 2 to represent the phase in each energy, in each mode. The phase of the oscillation in each mode. And then we could view these two like, well, how are the phases coupled? You could view it as a torus. So in one direction of the torus, that's the phase related to mode 1, and then the other angle is the phase related to mode 2. So we can kind of naturally view it as coordinates on a torus. So we're just geometrically representing it as motion on a torus. Technically, mathematically, this is called a two torus, but it's usual torus, surface of a donut. All right. But this is just for some particular choice of E1 and E2. For different choices of E1 and E2, we'll get a different torus. So this is for one choice of energies, the energy pair E1 and E2. So these the two energies are separately conserved, but of course they're both conserved in the system. The total energy of the addition of these two is also conserved. Maybe if we called this we'll call this 2E, it's total energy. And this total energy is equal to E1 plus E2. Because we have a 4-dimensional phase space, a total 4D phase space made up of 3D energy surfaces. And if you want to see how they're all connected, I'll give you this picture because it's interesting. This is showing the family of all tori, the invariant tori of the energy surface. And you'll see there's these curves that we're writing as C1 and C2. Those represent the two normal modes. So this is a collection of tori in the energy surface. All right, this is 3-dimensional, 3D energy surface. Oops. And then C1 and C2 represent the normal modes. The first and the second mode, respectively. Okay. I'm not going to have you draw anything like this for an exam. This is, I will have you do things like maybe find the frequency of something, but I'll give you some practice for that. And then you might be wondering, like, who cares? Why do I want to find out about modes? Who cares about normal modes? Well, if it's not exciting enough to you that the motion decouples, I don't know what to tell you. No, there's more to this. So maybe this will be the last section here. Why find normal modes? Often it's because you want to know which modes could be excited by an external time periodic excitation. So that's kind of the main thing from a practical engineering perspective. So this is to find out which modes are excited by a periodic external force. So, for example, the shaking of a building by seismic forces, earthquakes. I don't know if you guys know, but Goodwin Hall on campus has a whole bunch of accelerometers embedded in it. So you could actually find out the normal modes of this large degree of freedom building. And they're nowhere near being excited by the wind, but they can be excited by seismic forces. So earthquakes long distance away have actually been detected by the accelerometers in Goodwin Hall. So Goodwin Hall has become like this giant seismometer. It's kind of interesting. Let me show a figure to kind of illustrate this. Here's this is just a pretty bad schematic It's not so bad. It's a schematic of a like shaking something. So we're shaking the base down here. And let's say that the base, just for conceptual purposes, imagine the base of a building is being shaken by, it's going through some periodic distance b that changes with time. The building is like this flexible structure, so there's a mass on some flexible beams, and we're measuring the deflection x. So this is just this is the deflection of the building. So this is a really simple 1 degree of freedom model. Model for a flexible structure. So we've got the movement of the base. All right, B is a function of time, excites elastic motion of the structure. And what would that look like? Well, if we were to do a first order model, so it's just linear, you've got this mass m x double dot plus b double dot equals, we've got this part that has to do with the elasticity, and then a part that has to do with damping. So this negative kx is just a restoring elastic force. And then this is a damping. Damping is always present in the real world. We'll just assume it's linear damping. If the base moves with a amplitude b naught, so I don't know what that is, maybe a few centimeters, cosine capital omega t. So this is the frequency of oscillation. It's capital omega. Take 2 derivatives of that, you get negative omega squared b naught cosine omega t. We will call this term omega squared b naught. Well, that's the amplitude. So this equals negative a cosine omega capital omega t. This equation, we can rewrite it. X double dot plus 2 gamma x naught plus omega naught squared x equals a cosine omega t, where the natural frequency, we're calling it omega. Omega squared is k over m. So omega naught is the natural frequency of the motion, right? In the absence of anything else going on. This thing called gamma, it's called the damping parameter, and it's c over 2m. So this is the form I've written here. This is a standard way to write the damped harmonic oscillator. So this thing is called the damping parameter. And I mean, we're not going to go into great detail. You could look at how, if the damping parameter is small, there's some critical damping parameter that leads to different types of behavior. And now we've got this. So this left-hand side over here is the damped harmonic oscillator. And if there was no forcing, this would be equal to 0, but there is forcing. So now we've got this periodic forcing of the system. If you want external forcing, because it's external to this building. And we want to know, how does the driving frequency, omega, capital Omega, because that could change, how does that driving frequency affect the response of the system? And you might have seen, if you've taken a vibrations class, you've seen this. But you know, that's kind of what this, analyzing this 1 degree of freedom system can come down to. How does the driving frequency affect, I always get those two, it's affect the response of the building. Or let's just say the system. And how will we do that? We'll measure it by the maximum amplitude of X. So the amplitude of the X motion. So this leads to what's called a frequency response curve. And I will just show you a frequency response curve. Here is this frequency response curve. So this is frequency response. And why is that? Because down here, we've got the forcing frequency. If you can see it, it's the forcing frequency, capital Omega, divided by the natural frequency. And then this is the maximum amplitude divided by, you know, some constant. So this is called the response on this vertical axis, and this is the frequency. And then this is showing different values of damping. So when there's very low damping, you get this big response right at that natural frequency. Right, so this is what's important. You get the largest response by far. I mean, you get some response kind of near that natural frequency. So near the natural frequency, that is near the driving frequency divided by the natural frequency equal to 1. But it also depends on the damping. So if you have smaller damping, then you have less of an effect. I mean, larger damping. So as we go down here, this is larger damping. So this is what's significant. This is why you want to find the natural modes of a system. This is just 1 degree of freedom, but you can imagine if you are forcing a system, like a building, it's got many different modes. If you were to force it at some frequency, if you were close to any natural frequency, you could break the building. So a high response can lead to failure. And that is bad and could lead to damage. Right, maybe your building's not rated to shake a certain amount. So it could lead to failure, or imagine you're driving your car, you hit, if you've got an old car, you know, you hit that frequency and everything starts, you know, something starts shaking. You've hit a natural mode of your car. You found it experimentally by a frequency response curve. So we could say, or it could just be annoying. Right, things shaking. Shaking of your car at resonant speeds. I haven't even used the term resonant, but here we would say that omega, big omega close to omega naught, our driving frequency is in resonance. This is only showing right near 1, but there might be, you could have cases where if you were to drive the a system at twice its natural frequency, you'll still get a response. There's all kinds of things related to frequency response curves, and we're not going to go into all of that. I could show you experimentally. Here's a pendulum. I just tied a string around some kind of mass, right? So this pendulum has some kind of natural frequency. You can see it right there. I just let go. Now, I'll start it still, and if I move my hand at high frequencies, well, I'm much higher than the natural frequency. Nothing's really going on. If I move it at very low frequencies, again, I'm not stirring up oscillation here. But if I do it right at that natural frequency, my hand's not moving very much. So the amplitude's low, but I'm getting a large response. Frequency response curves in the palm of your hand. All right, so that is it.